Okay, so today we'll be going over this like a blog, Ultra-Scale Playbook. I'll read it line by line and we'll read it together, and wherever I need to look up online, like for example search up ChatGPT, I'll do that. Yeah, let's see how it goes. This is my first time doing something like this. Okay, let's go. So seems like they ran multiple experiments, and throughout they checked the GPU utilization. And okay, that's why it takes symphony of computing power. Elite research labs. Until recently was the exclusive domain of elite research labs. Why? Even now, right? I don't know. Oh, open source has transformed this landscape completely, but not completely. Yes, you can read there, but the motion training code. Yeah. So before this blog, I don't think there were any good resources at just one place, which would give you all the information of how the distributed large scale training of the huge LLMs took place. Remains and spread, yeah, so spread across a series of disconnected papers and private code. So I'll walk through the knowledge necessary to scale the training. Clusters used to train various techniques such as data parallelism. We'll discuss what data parallelism, tensor parallelism, pipeline parallelism, and context parallelism are. We will do that as well as zero and kernel fusion. Kernel fusion we'll also discuss, hopefully. Okay. We'll assume you have basic knowledge about and roughly familiar. Okay. Second part of a trilogy. So it seems like they have another blog on processing data for pre-training. Okay. Book is built on 3 general foundations. Quick intro. Oh, they have like activation memory usage breakdown, attention heads, hidden dimension, feed forward dimension, number of layers, number of transformer layers, sequence length. Okay, I mean we can play around with this, but it doesn't have any meaning for us currently right now. Let's go through the blog, understand how we can calculate by hand the activation memory and the total memory, and the memory taken by parameters, and the memory taken by the gradients, and the memory taken by the optimizer. Let's go through all of that, and then we'll have a better understanding of this. This is a nice widget, but doesn't mean anything to us now. Predict the memory usage during a training run. Oh, so they have a tool to do that. Predict memory. Oh, again, something like a widget. Okay. They have a clear code implementation. Okay. Real training. Okay. Cool. High level overview. Overview. All the memory usage, compute efficiency, communication overhead. Yeah, so memory usage is a hard limitation, as they say, because every GPU has a hard limit on the VRAM, right? So if the training step does not even fit in the memory, we cannot even proceed with training. Compute efficiency, we want the compute to be like the hardware resources to be utilized as much as possible. And also we want the GPU to spend most of the time doing computation rather than waiting for some data or doing some memory transfer. So waiting for data could be from the CPU or also could be from some other GPU. Communication overhead. Yeah, communication overhead is if we have multiple GPUs communicating with each other. The overhead of communication, like for example, the GPU 1 is waiting for GPU 2 to give it data. So that is an overhead of communication. Okay, we are at the first step, training on GPU. They also have some sort of an audio. You can listen to that if you want. Okay, so basic ML model training is a forward pass through all the layers. There's the forward pass in blue, backward pass to compute the gradients, where we start from here. We have, at the end of the forward pass, we have a loss function, and we do a backward pass to calculate the gradients of parameters in each layer as we keep going backwards. And to do that, oftentimes we need to store tensors that are like intermediate tensors, because for example, I can show you some visualization. No, I don't like this. Let's Okay, so let's say we have multiple layers. Okay, and this is the loss function. So loss function could be a function of this final output. Loss is function of output, and here each layer L1, L2, L3 has parameters, learnable parameters. Let's call them theta 1, theta 2, theta 3. So when we are at this layer, when we are back propagating, when we are at this layer, we'll want the dl by d theta 3, because once we have dl by d theta 3, we can, in the weight update step, we will do something like theta 3 is equal to theta 3 minus, where this is the learning rate. So this is why this is a simple optimization step, optimizer step. Some optimizers are more sophisticated than this, but let's just consider the most basic one. Okay, so to calculate dl by d theta 3, that is the gradient of this layer, what do we need? We might need this. Let's say this x1, x2, x3. We might need x3 also. So dl by d theta 3 would be a function of loss and x3. Similarly, when we are calculating dl by d theta 2, that is this layer, we need the gradient of loss with respect to x3, and also we need x2. So dl by d theta x2 is a function of x2 and dl by dx3. So when I was saying that to calculate the gradient of a given layer, we might need access to intermediate tensor, like for example x2 in this case. Why I am saying this is because to calculate the gradient of this layer, we also need this intermediate tensor, and while doing back propagation, we already have this dl by dx3 because we are back propagating gradients. Like for example, here we have the loss, and when we back propagate through this layer, we have dl by dx3, which can be used to calculate the gradients of L2. And when we back propagate through this layer also, we will have dl by dx2. So we don't need dl by dx3 in memory anymore. We can discard that, and we can keep dl by dx2 in memory. But for this layer, to calculate the dl by d theta 1 for this layer, we need access to x1 and dl by dx2. So you can see that when when we calculated dl by d theta 2, for that we needed x2, but we did not need x3. We needed x3 for calculating dl by d theta 3. So when we were, after doing the forward pass, we had to have access to all the intermediate tensors, that is x1, x2, and x3. But once we had backpropagated through this layer, we no longer need x3. We can delete it from the memory. Similarly, when we are backpropagating through L2, when we've done this step of backpropagating through L2 and calculating dl by d theta 2, we no longer need access to this x2. We can delete it from memory. So you can see that at the end of the forward pass, we need to store all of these intermediate tensors. So this is called activation memory, which can be a huge component of during machine learning model training. So yeah, just wanted to tell you what the activation memory concept is. Yeah, so this is, we have a forward pass, we have a backward pass, and during the backward pass we calculate the gradients of loss with respect to the parameters of each layer, and also we calculate the gradients of loss with respect to intermediate tensors because we want to backpropagate the loss. Okay, and finally, once we have the gradients, we have an optimization step. As I mentioned here, this is the optimization step. For a simple optimizer, we might have more sophisticated optimizers, but let's just consider this, where now after the backward pass, we already have the weights of all layers, and now after the backward pass, we also have the loss, the gradients of all the weights. So we can update this, an update step. We can update the weights according to this formula, and this is the updation step. Perfect. The batch size is one of the most important hyperparameters for model training, both model. Okay, yeah. Small batch size can be useful early in training to quickly move through the training landscape to reach an optimal however it is on the model training. Okay. So the concept of batch size was I think introduced in the mini batch size 2000. I don't remember. And I think some paper by either Jeffrey Hinton or by Elias Utskever, where they talked about, they called this batch size micro batch size, and they made arguments why using micro batch sizes instead of a single training sample makes more sense. So which is what they're saying here, a small batch size whose extreme case is just having a single sample in the batch, can be useful early in training to quickly move through, but reaching out to however further along the model training yeah. So if we have a very small batch size, the learning will be very, very noisy, so maybe the model will not be able to converge. Large batch size, okay, perfect. You can find a nice discussion on large batch training, empirical model. Okay, large batch training. And let's see, what is this? Let's read the abstract first. An increasing number of domains that has been demonstrated that deep learning models can be trained without sacrificing data efficiency. Oh, so their argument is that the limit of batch size differs from domain to domain. Image net can have batch size of tons of thousands. Really? Batches of millions in RLA. Okay. There is limited of by we demonstrate that a simple and easy to measure called gradient noise scale. It's the largest usable batch size across many. Find that noise scale increases as the loss decreases over a training run. Wait, noise scale increases as the loss decreases over a training run. Depends on the model size primarily through improved model compute efficiency. Okay, this is not very clear to me what they mean. Larger steps, smaller steps, less noisy gradients allow SGD type optimizers to take large larger steps leading to convergence in a small number momentum in a quadratic line. Okay, this is a big paper. We can read this later. Batch size also like the time it takes to train on a given small batch size. Okay, costly. Optimizer steps are costly in compute time. Why? Optimizer steps. Why? Because you just need to do an for a simple optimizer you just need to do a addition step, right? And even for something like Adam W, you first need to do an update step and then you need to update the two momentum parameters. That's it. Let's ask ChatGPT. And the total time to train will thus increase. Optimizer steps are costly. In my thinking, each optimizer step just needs an addition of the previous weight with the gradient of the weight from the current batch average gradient. Let's see what ChatGPT says. Excellent. Very, very encouraging. But is this supplementary? Let's unpack this from first principles. First principles thinking is very, very important. Elon Musk has said this. Right, that and just means everything that happens per iteration of gradient descent. Oh, really? so they when they say optimizer step, they mean each training step basically. Okay, so difference in terminology, I would say. Batch size. I was assuming their definition of optimizer step to be only the step where after the forward pass and backward pass, once we have all the gradients, we update the weights using the gradients we have. So in my head, this was what is optimizer step, but seems like they call the whole training step one training step. I mean, one iteration of forward, backward, and weight update for one batch. They call this one optimizer step. And they say it is costly in compute time. Perfect. Total time to train will thus increase compared to using a larger batch size. Oh, because if we have a small batch size, we need, let's say, for an extreme sample, we have a batch size of 1, and we have 1,000 samples, so we need 1,000 steps to cover one epoch. But if we have a batch size of 10, we'll just need 100 epochs, 100 steps to complete one epoch. Okay, seems like batch size, while it is important, it is not super important to hyper optimize for the ideal batch size. Batch size are commonly reported in terms of tokens rather than number of samples. Independent. Okay, so seems like what they're saying is in LLMs, we can have multiple tokens, right? So hello, how are you? One token, two tokens, token 1, token 2, token 3, token 4, token 5, and each token has a associated embedding vector with it, right? So the way we represent it is using token 1, token 2, token 3, token 4. So they're saying that if the batch size was 4, this would be one batch of this one here. Terms of tokens rather than samples. Oh. I think they mean by samples, they mean samples of documents. So each document, if we have 3 documents, that means we have 3 samples. So rather than saying that so rather than saying that we have a batch size and let's say we have multiple documents, and let's say three documents we call as we make them a part of a single batch. That means the batch size of 3. And they're saying that in LLM training, this is not the convention. The convention is that irrespective of how many documents we have, we don't consider the metric of how many documents we have in a single batch. We consider the metric of how many tokens we'll have in a single batch. So for example, this document has 100 tokens, this has 200 tokens, this has 300 tokens. So, but we do not care about the exact number of tokens. We just care about the tokens per batch. So let's say we define 50 tokens in each batch. 50. So now the batch size is 50 tokens. Is it? Batch size. Training on batch size and then batch size. Is it? I'm not sure. What do they mean by sample? I don't know. Let's ask ChatGPT. This line is talking about how batch sizes and why people report batch size and token instead of batch sample. Number of samples per batch. Okay. Sequence lengths vary. Each sample is a text sequence, but the length of each sequence can vary. Yeah. Even if you pad sequence, you can train with longer context length. So if you report batch size only as number of samples, amount of... Yeah, makes sense. So they're saying that if you define batch size in terms of the number of sequences processed per batch, this is not ideal because the sequence length can be different in different sequences. For example, if we consider one document to be one sequence, the number of tokens per document can be different. So the batch size would be different. Also, the number of tokens per batch would be different, although the number of sequences per batch would be the same. But in LLMs, all processing is done on token level. So we want the number of tokens per batch to be the same, not the number of sequences per batch. Report batch size and tokens. Batch size and tokens. Number of sequences into sequence. Number of sequences per batch, number of tokens per sequence. So this is actually bullshit. We don't even care about batch size into sequence. Just forget totally about batch size here. Just consider batch size tokens, where batch size tokens means number of tokens we are considering to be a part of a single batch. So we do not care about the abstraction of documents. We don't care about this abstraction at all. We just care about the abstraction of tokens. So for example, a batch might also span multiple documents. So if this is 3 documents and the batch size tokens in their language, or I'll just call it batch size. So if the batch size is 1000 tokens per batch, and this has 500 tokens, this has 200 tokens, this has 800 tokens. So in a single batch, these 500 tokens plus these 200 tokens plus 300 tokens from here, these would form batch 1. And let's say there's also document 4 with, I don't know, 500 tokens. This would form batch 1, like the green is all batch 1 tokens, and batch 2 tokens will get 500 from here and 500 from here. So this is batch 2 tokens. This is simple. I don't know why they complicated it so much. From here onward, we'll show the formulas for batch size in terms of batch size in terms of samples. So they're assuming that the number of tokens per sample is constant. Okay, whatever. I don't understand it fully. I don't understand this fully. Yeah, now there's what? Now they're reporting tokens per batch. Here you were saying that we'll show the formulas for batch size in terms of samples. Now you're saying tokens per batch. Okay. The batch size and the training corpus have been steadily increasing. Trained on tokens. Okay. We run to our first challenges when scaling the training to these large batch sizes out of memory issues. Doesn't have enough memory to hold a full batch. Yeah. This is a very, very important issue. Very, very frequently occurring issue. need to handle this properly. Okay, so what is memory usage in transformers? What are the components of memory usage in transformers? One is model weights, right? These thetas, where are thetas? Thetas. These model weights need memory to store. This is one. Model gradients, that is dl by d theta. During the backward propagation, we calculate the model gradients. This also needs memory to store. Optimizer states. This is only true for stateful optimizers. This is a stateless optimizer. We don't need to store any states for this optimizer. So this term, that is the memory required for optimizer states, for this simple optimizer is 0. However, we do not use this simple optimizer in practice. We use something more sophisticated in practice, like Adam optimizer or Adam W optimizer. So these optimizers have some momentum term, like a couple of parameters that we also need to store. So that is the optimizer state. And also we need to store activations, need to compute the gradient. And these activations are what I spoke about here. I told you about how we need to store x1, x2, x3. When we complete the forward pass, I told you how we need to store x1, x2, x3 for the backward pass. Yeah. You might think you could compute the memory requirement from exactly, but there are a few additional memory arguments that make it hard to be precise. CUDA kernels. Oh yeah. They typically require this much. You can... So they're saying that if you just do import torch, mind you that if you do import torch and do NVIDIA SMI, you might find that there is no memory being occupied because CUDA is not initialized yet. But if you do, after importing torch, you do torch.once, you define a tensor and move it to GPU, that is, define it as a CUDA tensor. Then CUDA will take up some memory, around 1 to 2 GB of GPU memory, even though this does not use 1 GB of memory. It is just like 4 bytes of memory. Some memory is used for... Okay, so we'll leave these 1 to 2 GBs or 2-3 GBs as buffer. We don't care about them at the moment. These items are stored as tensors. The shapes are batch size, sequence size, model. Yeah, so they're saying that we can have multiple precision levels that we can use. So the most common, maybe 3-4 years ago, was FP32, where all these things were kept in FP32 format, which has a lot of range and also a lot of precision. However, researchers found that we actually don't need this much precision. We need range, but we do not need precision. So they move on to BF16, which has, I believe, the same range but less precision than FP32. Let's check. Maintaining similar dynamic range to FP32 but reduced precision. Faster and use of the... Okay. So as I said, this format has less precision, and the reason we use BF16 instead of FP32 is because computations that we can do in BF16 are much faster compared to FP32. And you can extend this analogy further to FP8, where FP8 is even faster on hardware compared to BF16 operations. However, this has obviously you can imagine this has certain downsides. We need to make sure that the training still goes on well even if we are using FP8, because now we might face certain certain issues like loss divergence, or when gradients are being calculated, if the gradient is too small, like in terms of precision, then the weight will not be updated because FP8 does not have enough precision to be able to represent something like 0.00001 for the gradient. So it'll just round it off to 0. And that means when we do the gradient, when we do the weight update by doing theta is equal to theta minus dl by d theta, d theta, although it is supposed to be 0.0001, FP8 does not have enough precision to represent 0.001, so it rounds it off to 0. So theta is equal to theta minus dl by d theta, which is now 0. So theta does not get updated during training. That is a problem. Profiling the memory usage. Memory usage from the memory usage from these variables. Which variables? One simple way is to do this empirically and just measure. Which variables are they referring to? Are they referring to model weights, gradients, optimizer states, activations? I'm not sure. But anyways, we can, for all of them, we can find the memory, model weights needs, gradients need. These two are very simple, right? If you have, let's say for example, 1 million parameters, and each parameter is stored in FP32, that means 4 bytes per parameter. That means you have 1 million into 4, that is 4 million bytes that you need to that these parameters consume. And similarly for model gradients, if you're storing gradients in FP32, the memory required by gradients would be the same as memory required by model weights. That is also 4 bytes in this case. Optimizer states depends on the optimizer, but let's say you're using something like AdamW. So for each weight, for each parameter, you need to store two variables in AdamW optimizer. So, and let's assume you're using FP32. So instead of 4 megabytes, you'll have 8 megabytes required by the optimizer states. And activations are a little tricky because why? Because each when I said that you need to store x2 here in this layer, this is not fully true because there are certain operations where you do not need to store. There are certain operations, like let's say L2 is an operation. So there are certain types of operations where to calculate dl by dx2, which is a function of I said that dlx is a function of this and this, right? But there are certain operations where dl by dx2 is just a function of dl by dx3. So we do not even need to store x2 in that case. So activation memory is, I would say, model dependent, and we'll see how we can estimate activation memory. Providing the memory, we see that memory is not a static thing, of course, but varies widely during training and during a training step. Check out for a walkthrough of how to profile a model. Okay, we can do this later. So this is the memory profile of first 4 training steps of Llama 1 billion model. This is the forward pass. Why does it stay constant here? We will see that. And I assume this is the backward pass. Why is it constant? This makes sense to me, but this does not fully make sense to me. Maybe some caching after the forward pass. Since this is the first batch, PyTorch has to do some sort of caching, so it takes some time. I don't know. Let's see if they provide any explanation for this. Yeah, first step looks very different from the subsequent ones, but before we get to that, let's take a look at the general. First, the activations increase quickly. Yeah, because as as we discussed, while doing the forward pass, we need to store the intermediate tensors for the backward pass. So as we keep going forward in the forward pass, we keep building up these intermediate tensors in the memory. So that's why the memory keeps going up. First, the activations increase quickly. As we do the forward pass, then during the backward pass, the gradients build up. Yeah. So and as we do the backward pass, we can keep freeing up the intermediate tensors that we originally stored for the backward pass as we go through the layers during the backward pass. However, we also need to now keep storing the gradients during the backward pass. Yeah. As a backward pass, the stored activations used to are progressively cleared. Yeah, this is what I said. Finally, we perform optimization, during which we need all the gradients. Yeah, and then update. So we keep the gradients keep building up until we have done the whole backward pass, and and then we do the optimizer update. This is I know I'm pretty sure this I know what this is. This red part is because once we have the first step of the optimization, once we have the first batch, that is the optimization step, done, we have now, after the first step, we now have the the optimizer state for each parameter. We have it, so we need to store it for subsequent runs. So this is the optimizer step that we store for subsequent runs. What else? Yeah, as mentioned, the first learn activations and plateau for. Yeah, why do they plateau? I don't know. PyTorch caching allocator does a lot of prep work preparing memory allocations. Oh, caching allocator, somewhat related to what I said. Memory allocations. Yeah, because in the first step they don't. While doing the first step, PyTorch does not know how memory allocations would work. So after it does the first forward pass, it sort of internally prepares memory allocations so that subsequent batches can then just use the memory allocations, because in every batch the memory allocation pattern would be the same. So the subsequent batches can just reuse the memory allocations of the first that PyTorch learned from the first step, so that they don't have to search for free memory blocks in the subsequent steps, which also speeds them up. Okay. Oh, interesting. Let's see Zach's blog. Metrics. Guide to PyTorch CUDA caching allocator. Which is steady state when the program runs without needing to request memory. Oh. Okay, so seems like we do not want to use CUDA free, like APIs like CUDA free and CUDA malloc too often, because they have some synchronization overhead. So what what PyTorch does is every time once it does the first, once it requests a memory block from CUDA, once it has some memory blocks from CUDA, it figures out that in subsequent steps it will reuse these memory blocks that it has requested from CUDA. And since it does not want to since we do not want to make multiple calls to CUDA API for CUDA malloc and CUDA free, because they have some sort of overhead, once we get the memory block from CUDA, PyTorch keeps control of them and manages the memory by itself. So this is why here, this is PyTorch doing some magic and figuring out how it can manage the CUDA blocks that it already has access to. Why not just request all GPU memory and manage it inside PyTorch? Yeah, so this is what TensorFlow does by default. And this is irritating because sometimes you have other libraries like cuDNN or cuBLAS, Cutlass, all of these libraries, which they do not know what is happening with TensorFlow, right? TensorFlow already, let's say your GPU has 80 GBs of VRAM. TensorFlow already takes control of majority, like 78 GBs of that VRAM. So what is left is just 2 GBs. But there are also other libraries like Cutlass, cuBLAS. You might, if you're calling TensorFlow functions, they have a mechanism to let TensorFlow's memory allocator. So for example, let me give you an example. Let's say you're calling TensorFlow's convolution operation, and TensorFlow's convolution operation calls cuDNN. Now, if you call TensorFlow's convolution operation, and TensorFlow has to call cuDNN. So TensorFlow's memory TensorFlow will, since TensorFlow has access to all the GPU memory, it will pass the GPU memory pointer to cuDNN, and cuDNN can use the memory from TensorFlow's memory, from the memory that TensorFlow is managing. So cuDNN, in this scenario, cuDNN does not need access to additional memory because TensorFlow is giving it memory from its own memory pool. That is basically the whole GPU memory. But the problem lies in the case where you call some cuDNN kernel not through TensorFlow. So you do not, what I mean by this is within the TensorFlow program, you try to independently call a cuDNN kernel. And if you call independently the cuDNN kernel, it does not have any idea about how TensorFlow is managing the memory pool for it. For the cuDNN kernel, all it sees is 2 GBs of vacant GPU memory because 78 GBs is taken by TensorFlow. So it tries to get memory from the 2 GBs of GPU memory. And a lot of times it might get out of memory error because 2 GB is not enough for certain operations. And you can imagine that instead of one kernel, what if we had multiple, like tens of cuDNN kernels? Then we'd definitely get a OM error. The way we deal with this in TensorFlow is artificially limit the memory that TensorFlow has access to. So we can, for example, limit TensorFlow to use only 60 GBs, and now we have 20 GBs of memory available for everything else. So this, as you can imagine, this requires a lot of manual tuning, so which can be frustrating at times. So PyTorch, and why this is but the plus side of this is TensorFlow, since TensorFlow has access to all the memory, it can better manage the memory more efficiently compared to PyTorch, but is kind of irritating sometimes. PyTorch. Yeah, so this is what I was saying. Users might mix PyTorch and other CUDA accelerated libraries we do not know about. Instead, if PyTorch ever use n bytes of memory, we will continue to keep that n bytes cached until. Okay, perfect. Oh, so they're saying that under most circumstances, we do not need to think about how the allocator works, but certain cases we do need to care about how it is working and why we got an out of memory error. Particular set of adversarial allocations might prevent it from reaching a steady state. Okay. Okay, this is pretty detailed. We'll skip this for now. But very nice blog. I really like this blog by Zach. Now that we have a first view of memory, let's see how scaling up training is often a question of maximizing compute efficiency while keeping the optimizer memory requirements of the constraints of memory. Start with the first three. Model weight, gradient, and optimizer. Pretty easily estimate the memory need for them. Simple transformer LLM number of parameters given by this formula. Actually, we can estimate the number of parameters in a given transformer, where the parameters of transformer are, like, we have L layers in the transformer, H is probably the number of attention heads, V is the vocabulary size. No, H is the hidden dimension. V is the vocabulary size. Yeah, I think so. But I mean, it is easy to estimate the number of parameters given that you know the transformer architecture and what all of these stand for. Seems like they have this. Yeah, so they derive the number of parameters by seeing the number of parameters in each layer of the transformer. So you can imagine that the transformer architecture has multiple transformer blocks or transformer layers, and within each transformer layer there are multiple sublayers. So there might be a multi-layer perceptron layer, there might be a Galo activation layer, there might be an attention layer. These three are the major layers, I believe. And also outside of the transformer block, like the full block, we have while inputting to the transformer block, we have the embedding layer. Yeah. Oh, and also within the transformer, each transformer layer, we have layer norm also. So calculating the parameters for each sub network and aggregating them across all the sub networks and across all the transformer blocks, we can get a formula for the total parameter count, which is this. Oh, they mention H is the hidden dimension, V is the vocabulary size, and L is the number of layers in the model. Yeah, as I said. Note that you can see that the term will accommodate the H squared term. Yeah, so this is a problem, right? H is a quadratic term. N is proportional to H square. That's the number of parameters is proportional to H square, where H is the hidden dimension. Yeah, so this is what we discussed earlier, where if we use Adam, which has momentum and variance to be stored, like two values to be stored for each parameter. This is the memory if we use FP32 training. If we use mixed precision training, this would be BF16, so 2. Gradient would be BF16, so 2. But we also, in terms of if you're using FP16 or PF16, a lot of times to keep the training stable, we also keep a master copy of the gradients. Oh, sorry, master copy. We keep a master copy of the parameters, right? Because we update the So we also keep a master copy of the parameters. So along with this parameters in 2, because in BF16 we also keep a master copy of the parameters in FP32. Oh, so so we're not saving any memory in FP16, BF16 compared to FP32. Huh, so why even use BF16 instead of FP32 if we're not saving any memory? Because although we're not saving any memory in terms of these first three terms, these first three terms, the activation, since now each activation would be in BF16 instead of FP32, the memory required for activations is halved, which is a significant memory reduction. Master weights, as I said. Still advantageous though, as computing. Oh yeah, also computing the forward and backward pass can happen. The computation itself can happen in BF16 instead of FP32, and those computations are much faster compared to FP32 computations. So the first benefit is faster computation because it allows us to use optimized lower precision operations on the GPU, which are faster, and reduce the activation memory requirements. Yeah, as I said. Okay. Memory for activations, which is the fourth term. We already covered the first three terms. Now we cover the fourth term, memory required for activations. It's a bit more complex to compute than for the weights gradient in part because they depend on the inputs of the model. Inputs of the model. Why inputs of the model? No, they should depend on the model architecture, not the inputs of the model. Right. Let's ask ChatGPT. Why does the activation memory required to store the activations in LLM training depend on the inputs of the model? In my opinion, it should just depend on the model architecture, that is the layers being used in the model, and there should not, and it should not depend on the inputs, i.e. there should not be any data, input data dependency. Let's say ChatGPT. It'll probably say very good question or excellent. Yeah, excellent. This is very you're right. But there's still a dependence on the inputs. And that okay, what are activations? Here's where the input data itself starts to matter. Variable sequence lengths in LLM sequence are not all the same length. Text chunks of different lengths. Yeah, but I mean, my claim is that they're not dependent on the input, the data present inside the input. They're dependent on the input shape, right? So you should write they're dependent on the input shape, not the input itself. Yeah, into input shape, not the input itself. Like not dependent on the data inside the input. It is dependent on the shape of the input. Yeah, so that makes sense. Okay, some minor terminology difference. And they calculate the activation memory required. Do you want me to go through this, the derivation of the activation memory? Seems like it does not load, does not want us to be able to calculate the activation, but I'll tell you how to calculate the activation through these words. The activation memory depends on some factors, one of which is if we are using activation recomputation or not. Let me introduce you to the concept of activation recomputation. Okay. Let's say this is for a transformer. This is transformer block 1, transformer block 2, transformer block 3, transformer block 4, transformer block 5. Input, output. X1, X2, X3, X4, X5. Now, in the naive setting, we would store X1, X2, X3, X4, X5 for the backward pass. So the activation memory would be the memory required for X1 plus X2 plus X3 plus X4 plus X5 plus within each transformer there are multiple layers, right? So layer 1, layer 2, layer 3, layer 4, layer 5. So X1, X, XA, XB, XC plus XA plus XB plus XC plus XD plus XE into the number of transformer blocks, 6 in this case. So you can see that these can be very irritating because we need to store the activations for each layer, and this amount could be very high because if the transformer architecture is deep, then all of this would be very high. So we'll get an out of memory error. So what we do instead is to not store all of this, just store this. And when you need activations inside here, while doing the backward pass, let's say you're trying to calculate the dl by d theta of this layer. For that you need the activation of this, and you need dou L by dou x3. Dou L by that is dl by d x3. dl by d x3 you already have because you're doing the backward pass and you're here. But you also need this, let's call this x2, or let's call this xi, x intermediate. You also need x intermediate. How do you get an x intermediate? Because you did not save x intermediate, right? The way you get x intermediate is you have x2 because you saved x2 here, you saved x2. You do a mini forward pass again, like a redundant computation. So when you do a mini forward pass through this transformer block, you have all of these intermediate tensors, and you store all of these intermediate tensors only for this transformer block. So rather than having into 6, you have xa plus xb plus xc plus xd plus xe into 1, because at a time you'll have just one transformer block for which you store these intermediate tensors. This is the magic of activation recomputation. However, you can imagine that there is some computational overhead because you're doing the forward pass for each transformer block again. So you're trading computational time with memory. You're saving memory, but you're trading computational time in activation recomputation. For the exact derivation, you can follow the original NVIDIA paper on recomputation. Oh, so they assume activation recomputation. Let's see what this paper says. Training is one of the important significantly accelerate training of large tasks. Activation and recording commonly used. Is it even recording? Yeah, it is recording. Training large transformer. How does significantly accelerate training of large transformer? Storing activations. Show motion. Sequence parallelism and selective activation. Activation memory. Oh. So in this paper, they're trying to, rather than storing the activations for just the inputs of the transformer block, they are trying to do something smarter. Because here, if we store the activations for the inputs of all the transformer blocks, we also need to recompute all of this, right? So they're trying to do something smarter, where ideally you would want to save an activation which does not require a lot of space, right? So you don't use a lot of memory. But also, the additional computations you need to do, they should not be very computationally expensive. So you need to find a type of layer. If you checkpoint or save the activation of that layer, then the memory required for saving that activation should not be very high. But also the additional computation you need to do to compute the other activations should not also be very high. So they are analyzing the activation memory per transformer layer. So in the attention block, they're calculating how much activation memory each layer takes, and also in the MLP and also in the layer norm. This is the activation per layer. Selective activation recomputation. So in selective activation recomputation, as I said, instead of storing the activation for each for the inputs to each transformer block, they do something smarter. This is kind of too long. Let's discuss this in a separate paper discussion, I would say. But this is definitely very interesting. I would want to read this. Anyways, so there's the formula of the activation. But the key takeaway from this, what is the key takeaway from this? The key takeaway from this, do they oh, they explain activation recomputation, is it? Interesting. Okay, I think this video is already long enough. Let's discuss the other parts in another video. It was a pleasure, guys. Signing off for today.